Right now it looks like, I think next Monday is Columbus Day, is that correct? So it looks like the exam will be next Wednesday. That looks like the, not this Wednesday, next Wednesday. What's it, you want another one this Wednesday also? No, you want it too.
We do a practice.
What's that?
We do a practice this Wednesday, or like the real thing.
Yeah, I'm not sure I want to make it 2 exams. Thank you. Okay, so if you remember, the material from the first exam went up until, but not including Laplace transforms. So I think it's chapter 3, the end of chapter 3. And you had a number of homeworks there, I think, that we did today, that which is the last preparation for the exam. I'm happy to set up a recitation. We can talk about that at the end of the hour, in another time. Or actually, we could do it during my office hours, but no one ever shows up to office hours. But if people show up to office hours, we can make it a recitation. I could just get a classroom, we could make a recitation. What we did so far, if you remember, is before we start actually doing control, we're learning how to model in the real unsteady state land, how to model systems that are related to relevant for chemical engineering, as opposed to modeling them steady state, we're modeling them unsteady state, which is new for the undergraduate curriculum. It's really the first time you come across unsteady state models, other than for the batch reactor, which you sort of fly over in kinetics, and it's not considered in great detail because you're usually interested in steady state flow reactors. Up until now, we've done that modeling, and the way we've solved those equations is by the methods of ordinary differential equations. And we saw that there was a lot of algebra involved. In fact, we found that we typically got linear first order differential equations in many situations. And when the situations weren't linear, we linearized them because we know how to solve linear equations. So we took nonlinear equations and we approximated them by linear equations, and then used methods, and I can just erase here, but we're up here for about 3 or 4 classes, of the generalized solution of linear first order ordinary differential equations, which we can solve exactly. So that's why we like them. The problem was, not that it was a big problem, but we got it involved a lot of algebra. And a lot of times, typically, the more you have to write, the more likely you are to make a mistake. It turns out there's another method to solve these types of equations, not just first order, but any order differential equations. And those are called transform methods. And there are many reasons for using transform methods, but the main reason, the utility, and we're concentrating on the Laplace transform, but there are also Fourier transform and Hankel transforms. There are many transform methods. The whole point of a transform method is that you can take a differential equation or an integral equation, an equation with derivatives and or integrals in it. And when you transform it, the derivatives and the integrals disappear and you're left with an algebraic equation. If you do full transforms. You may have a partial differential equation and only do a transform on one of those variables, and then you're left with an ordinary differential equation. The idea is, once you transform the equations, you get much, much easier equations to solve, ones that you probably know how to solve in a fairly straightforward manner. And then what you need to do is, once you solve them, it's in the funny transform variable. So hopefully you can transform back to the variables you're interested in. I was planning on photocopying something for you, which I, of course, forgot to do. I will do it for next time, but you have it in your textbook. And that's on page 100. I asked you to look at it. It's a table of Laplace transforms, which is a table that has f of t, the function in the time domain, and f tilde of s, which is its Laplace transform. So what we said last time, we defined the Laplace transform is a form of definition. It's the integral from 0 to infinity, assuming certain things exist, of your function f of t e to the minus st dt. Notice once I've integrated dt, there's no t left, and the result is a function of s. And I could either write it as L of f of s, L of f, which is Laplace transform of f, Whereas often, just for shorthand, I'll write an F with a tilde on top as S. Sometimes people are sloppy and they'll leave the tilde off, and I find that confusing. F is a function of t. F tilde is a function of s. If I have f sometimes a function of t and sometimes a function of s, that just confuses everybody. So, I'm going to try to always put the tilde on. And we noted that s can be complex, and we can represent the complex number either as x plus iy or as r e to the I theta, where e to the I theta is a shorthand for cosine theta plus I sine theta. And I assigned last time a homework for you to show that this makes sense, this notation. In fact, it's the only definition of e to an imaginary number that is consistent with what we know about e to the x. In particular, that e to the I theta 1 times e to the I theta 2 is e to the I theta 1 plus theta 2. No other definition works. We noted that Laplace transform is linear because it's an integral. If I have the integral of f1 plus f2, that's the integral of f1 plus the integral of f2. Similarly, if I have a constant here, and multiply f by constant, the constant can come out of the integral. And then I noted officially the formal definition of what the inverse is. And that requires an integral in the complex plane, which you have not learned how to do because you haven't taken complex variables, unless someone has. So since you've never learned how to do this, we're not going to do it this way in this class. If you're ambitious and you want to learn, I'm happy to help you with that, but that's not part of the syllabus of the course. The way we're going to do it is we're going to just use the table. Your textbook has a table that's one page that has 18 different pairs of f of p and f tilde of s. It has 18 different pairs. You can find other tables in more comprehensive books that may have 100 or 150 pairs. So depending on how complicated your system is, this may not be enough. We're going to illustrate, so what we're going to start out today with is we're going to prove some properties of Laplace transforms, which, if you remember, I said that derivatives and the integrals disappear. Well, you shouldn't believe me. We're going to have to prove that when we do the transform. And then we'll look at some other problems. So today is going to be properties of Laplace transforms that I've claimed are true. We're going to show that they're true. And then a couple of examples. So that's the basic outline of what we're doing today. We'll get to other things a little bit later on. Let me just note something. There are only 18 transform pairs on this table. And you might say, 18. 18 is not a big number. How is that going to be enough for this course or for anything? And in reality, it's not enough. You need many more. But even the 18 is not so bad because, or are not so bad, because when you solve a problem, you may get a big mess as a big function of s, a big complicated f tilde of s. But many times you could break up that big mess into a sum of terms, where each one of them is in the table. So you can't expect all possible functions to be in the table, but a lot of times if you find a complicated function, if you break it up into the sum of simple functions, you could find them in the table. And that we probably won't get to until next class. That's called partial fractions. So that's sort of coming attractions. You know, like in these TV series, they want you to come back next time. So they tell you something to make you eager to come back next time. All right, so let's look at a few lists that I want to do. Yeah. So let's f be a constant. So this is, so then f tilde of s is the integral c times e to the minus st dt 0 to infinity. And let's go through the details of that. This is sort of, I can pull the c out. This is equal to c times the integral of 0 to infinity e to the minus st dt. And what's the integral of e to the minus st dt? All my math whizzes here? Come on, let's get a volunteer here. This one's not a hard question. You just pull the math out.
I think it's e to the negative s divided by negative s.
divided by, yes, thank you. So it's e to the minus st divided by s negative, and I'll use the negative to switch the limits. So I use the negative to flip the limits, thank you. So at 0, this is just 1. At infinity, it's 0. So this is just c over s. That's the first one. What's the next one that I want to do? Next one is theta. So is everyone familiar with the Heaviside function? So the Heaviside function is the function, if this is 0, and let's get blue chalk. It's a function that's 0, so this is theta of t. Let's do it in blue. It's 0 for t less than 0. And it's 1 for theta greater than 0. And at 0, usually the convention is we say it's a half. But we think of it as the step function. So that's called the Heaviside function. And you know, it kind of looks like one side is heavier than the other, but it's actually named after Oliver Heaviside. I don't know how heavy he was, but so let's look at that. So now if I have, so let's let f of t equal to theta of t, then f tilde of s is, was there a question? F tilde of s is the integral from 0 to infinity of theta of t e to the minus st t. But theta of t for everything greater than 0 is just 1. So this is just equal to the integral of e to the minus st dt, 0 to infinity. Which we were just told that that's just equal to e to the minus st over minus s. So I just use the minus to flip these. And this is just equal to 1 over s. Let's look at another one. Let's look at the Heaviside function theta of t minus tt. Yes? Can you just remind me, I'm sorry, I'm terrible with names. I have to hear names 1,000 times.
It's
Lisa.
Lisa. How do you get rid of theta of t?
How did I get rid of theta of t?
Yeah.
Because theta of t is 1 for t greater than 0. So as well, because the region of integration goes from 0 to infinity, it's all non-negative, and that's where theta is equal to 1. So it's just equal to 1 there. So maybe I should be explicit and call this a little 1 here. Now theta, and this relates to Lisa's question, theta of t minus tp, let's just plot that. Here's 0, here's tp. Theta of t minus tp, here's 1, looks like this. So there, it's 0 for t less than 0, t less than tp. So let's look at the integral f tilde of s is equal to the integral 0 to infinity e to the minus st theta of t minus tp dt. And this one is a little different because theta is 0 for t less than tp. So for t less than tp, the integrand is 0, so I only need to integrate from tp to infinity, e to the minus st times 1 dt. Because for t less than tp, theta is 0. Well, so now I do the integral, and here again I get e to the minus st over s, and I use the minus line to flip the limits, tp to infinity. And here, you notice I get e to the minus stp over s. Now let's construct an interesting function. Let's construct the following function. I would like to construct a function from t to tp, to t plus tp. T plus epsilon, what we call it. t to t plus epsilon. And I would like to make its height 1 over epsilon. So if I have a rectangle that goes from t to t plus epsilon and has a height 1 over epsilon, what's the area of that? Volunteer? What's the area? Yeah?
T over epsilon.
First name?
Agatha.
Agatha. So it's a width epsilon and a height 1 over epsilon. So what's the area?
T over epsilon.
I have a rectangle. The width is epsilon, the height is 1 over epsilon. It's 1. Okay, so if I want to construct this, one way of constructing that is I can call that f of t be equal to, well, this looks, so it's 1 over epsilon. But then this looks like, let me shut this off. Amazing how everyone calls me when I'm teaching. This looks like a theta function minus another theta function. So this is theta of t. And actually, why don't we call this Tp and Tp plus epsilon? So this is theta of t minus Tp minus theta of t minus Tp minus epsilon. Or why don't we put parentheses around this? And Tp plus epsilon. So this is the step function in Tp minus the step function in Tp plus epsilon. Is that clear? So I've constructed this function, and let's see what I get. So what is f tilde of s? Well, I already know what these guys are. So I have a 1 over epsilon, and I have theta of t minus Tp. Well, I know what the f tilde of that is. That's just 1 over s times e to the minus STP. And then I've got the transform of this, which is again 1 over s times e to the minus STP plus epsilon. Is that clear? So I can factor this out, e to the minus STP times 1 minus e to the minus s epsilon divided by s epsilon. You'll see why I'm doing this in a second. Now, just for fun, let's take the limit as epsilon goes to 0 of f of t. And f of t also depends on epsilon, where this is my f of t. Well, the f of t also depends on epsilon. First, let's think physically what's going on, geometrically. As epsilon goes to 0, the rectangle gets thinner and thinner, but it gets taller and taller. But what happens to the area? No matter what epsilon is, what's the area? I can't hear anyone because of the noise. 1. The first name? Oh, Robbie. I didn't even recognize you with your mask on. I do. So as epsilon goes to 0, it gets thinner and taller, but the area stays 1. So in the limit, that's the limit, this becomes infinitely thin and infinitely tall. So it's no longer a function. Because any normal function, if I have a value of infinity at one point, it should have 0 area. But because of the way I'm taking this limit, this is called a generalized function. It's not a function, it's a generalized function, which I'm not going to fuss too much about. But it's infinitely thin and infinitely tall, but the area is 1. Well, if that's the case, then let's look at the transform. The transform is the limit as epsilon goes to 0 of f tilde of s. And what's that equal to? Well, this has no epsilon in it, so that just comes along for the ride. And now what I need to do is I need to take the limit of this thing as epsilon goes to 0. Well, when epsilon goes to 0, I have 1 minus 1 in the numerator, and I have, which is 0, and I have 0 in the denominator. How do I resolve 0 over 0 from calculus? Whose rule do I use? L'Hopital. So I'm going to take the derivative of the numerator over the derivative of the denominator. The derivative with respect to epsilon of 1 is 0. The derivative of minus e to the minus s epsilon with respect to epsilon is derivative. You just pull the mask. Minus s e to the minus s epsilon times minus 1. So it's in the derivative, so I need to take the limit as epsilon goes to 0. The derivative of the numerator is s e to the minus s epsilon. And the derivative of the denominator with respect to epsilon? S. And the limit, what's the limit as epsilon goes to 0 of e to the minus s epsilon? Can't hear anyone. What's the limit as e to the epsilon goes to 0 of e to the minus s epsilon? In the back? 1. So this is just e to the minus st. So, and this limit is called delta of t minus dp. Where delta is called the Dirac delta. And the generalized function is often called a distribution. That means it's not really a function, it's something more general, it's a distribution. And distributions come up in probability all the time. That's why you may have heard it before. Dirac, Paul Adrien Maurice Dirac, P.A.M. Dirac, was one of the great physicists of the 20th century who came up with this and saw it was super useful. Basically, there's the famous Dirac equation, which is the first equation for relativistic quantum mechanics. And rather than 3-dimensional space, he works in 4-dimensional space with x, y, z, and ct. Very famous physicist, and I think he only died in the 80s, even though he was quite old. British physicist. And let's notice something. Notice that when I integrate, so when I take the Laplace transform, note, what I did when I took the Laplace transform is I took the integral of e to the minus st delta of t minus dp dt from 0 to infinity. This was delta tilde of s. And notice this was equal to e to the minus stp. Notice something funny here. This integral was the integral of an exponential times delta. This could be at all values of t. And I just got the exponential back at tp. Let's see if that happens in general. So let's look at the integral from 0 to infinity of a general function, say g of t, delta of t minus dp, dt. Let's just see what that is. This is just for fun. Let's see what that is. Well, this we said is the limit. It's the integral from 0 to infinity, g of t, times the limit as epsilon goes to 0 of 1 over epsilon times theta of t minus, sorry, I'm running out of space here, t minus dp minus theta of t minus tp plus epsilon. dt. Sorry I crammed it in that corner of the blackboard. Basically, I just copied this thing over. Now, let's see what that is. Let's notice that in the limit, when epsilon gets small, this thing gets very thin. If G, so here I'm assume that G of t is continuous at Tp. So it's not making any big jumps at Tp. G of t is continuous. Then what happens? If G of t is continuous and the region over which, and I'm multiplying it by something, that's 0 everywhere to the left of t, and everywhere of Tp, and everywhere to the right of Tp minus epsilon. So I'm only considering the value of the function between Tp and Tp plus epsilon, because that's the only place where this thing is non-zero. So if I do that, then first of all, so I have this quantity is the integral from Tp to Tp plus epsilon. That's all that's left. And I have a 1 over epsilon. G of something dt, G of t. And what I'm going to do is I'm going to pull the limit outside of the integral. Is that legitimate? The limit was inside the integral. An integral itself is a limit, so I'm switching the order of taking the limits. That is not obvious you're allowed to do that. In mathematics, you have to prove that you can do that. Sometimes you get the wrong answer. There's a theorem called Fubini's theorem that basically says if both ways of doing it give you a finite answer, then they're the same, then you're allowed to do it. But on occasion, one way of doing it gives you an infinite answer, another one gives you a finite answer, and they're obviously not equal. But this is not a math course, this is a control class, so we're not going to worry about that. And let's notice that over this very tiny region, when epsilon gets small, G of t doesn't change much because it's continuous. So I can approximate G of t by G of Tp. In which case, I can pull G of Tp out, and I can pull the epsilon out, and now I have the integral from Tp to Tp plus epsilon dt. And I have the limit as epsilon goes to 0. Well, this integral is just Tp plus epsilon minus Tp is epsilon. The epsilons cancel, and I just get G of Tp. So what did we note? What we found was the integral. So therefore, one property of delta is the integral from 0 to infinity of G of t, delta of t minus Tp, dt is just G of Tp. In other words, when I integrate a function, any function, G of t, as long as it's continuous, times a Dirac delta, I just get the function back at the point where the Dirac delta, where the impulse is for the Dirac delta. I pick out one point of the function. Now, of course, this only works if Tp is greater than 0. As long as Tp is in the domain of the integral. Are there any questions on that? Seem to be belaboring stuff that usually should go faster. Anything else? Oh, yes. Questions? Okay, let's do a couple more. Let's do e to the at. So let's say, what number am I up to? 5. F of t is e to the at. Then f tilde of s is equal to the integral from 0 to infinity, e to the at, e to the minus st dt. So that's equal to the integral from 0 to infinity, e to the minus s minus a t dt. And this is just equal to the exact same rule we did here. This is This is just equal to 1 over s minus a with the minus sign, e to the s minus a t from infinity to 0, which is just 1 over s minus a. Next, 6. Let's do f of t is sine t. Or should I do sine omega t? Which one? Sine omega. If you have any questions on the algebra, just ask me. So I've got f tilde of s is equal to the integral from 0 to infinity, sine omega t, e to the minus st dt. Well, this one I can't do directly, so I'm going to integrate by parts. So I'm going to let this big thing be u, and this be dv. Or I could do it the other way around. So du is equal to omega cosine omega t dt. And v is e to the minus st over minus s. So then I have f of that, f tilde of s is equal to uv. So e to the minus st sine omega t over minus s from 0 to infinity minus the integral of v to u. So minus and minus is a plus, e to the minus st, 1 over s, omega, cosine omega t. Now let's evaluate this. At infinity, this is 0. At infinity, this is 0 because the exponential is 0. And at 0, it's 0 because the sign is 0. So this is just comes out. And so I just have this thing over here. And now let's do the same thing again. Let's let this thing be u, and I'll include the minus sign in the u. And dv is again this thing. dv. Okay, so du is equal to omega sine omega t dt. So I take the derivative cosine, I get minus sign, so I kill that minus sign. Sine omega t dt. And v is again the same thing as before, e to the minus st over minus s. So f tilde of s is equal to, it's equal to, well, the omega over s comes along for the ride. And I need to take uv, that's cosine omega t, times e to the minus st over minus s, 0 to infinity. Minus the integral v to u. So minus the integral e to the minus st over s, minus is cancelled, times omega sine omega t. And let's see what this thing is. At infinity, this is 0. And what happens at 0? At 0, this is 1. So let's see. So I have omega over s times, at infinity, this is 0. And at 0, this is 1 over s. So I've got 1 over s, if I did that right, 0, and minus omega over s times the integral from 0 to infinity, e to the minus st, sine omega t. This is f tilde of s. But notice f tilde of s is the integral, is exactly this integral. So this is also f tilde of s. So I have f tilde of s is equal to omega over s squared minus omega squared over s squared, f tilde of s. So I can solve for f tilde of s. So I add this to both sides, factor and divide, and I get f tilde of s is equal to omega over s let's just make sure that's the right answer, that I haven't made any algebraic mistakes. Omega, yeah, so let's multiply top and bottom by s squared, and I get omega over omega squared plus s squared. That's the correct answer. Any questions on that? Okay, so now we're ready for the fun ones. And of course, so we've just proved a handful of the ones on this sheet. You can prove them all. Let's do the more fun ones. Number 7. Let's look at the df of t dt tilde. Let's do the tilde of that. So take a Laplace transform of the derivative. So that's equal to the integral from 0 to infinity, df dt, e to the minus sd dt. For f is any old differentiable function. Again, you don't have to worry about copying down every word because you're going to get, I post the pictures on Blackboard. So this one, I'm going to integrate by parts. I'm going to let this be dv, and this thing be du. So du is minus s e to the minus s t dt, and v is just f of t. So df tilde dt, df of t dt tilde, is equal to uv, that's e to the minus st, f of t, from 0 to infinity, minus the integral of du, minus, which is now plus, s times the integral from 0 to infinity, e to the minus st, f of t, dt. So let's evaluate. At infinity, the exponential is 0. And at 0, the exponential is 1. So this is equal to f of 0 with the negative sign. And this thing is just f tilde. So what we find is the f dt tilde is equal to s f tilde minus f0. Notice, whenever I have a derivative, it disappears. I just multiply by s. Magic, no more derivative. So if I have a differential equation, that disappears. And I can extend this to higher order derivatives. I can do the same thing for second order derivative. I just did. So for d squared f dt squared tilde, I just integrate by parts twice. Etc. For third derivative, I integrate by parts 3 times, etc. Any questions on that? Well, let's do the integral. 7. How many are we? 2, 4, 6, 7, 8, 9, 10, 11, 12. Okay, there are only 25 of us here. I'm going to have to start taking attendance. You guys are good, but everyone else is going to be, if they stop coming, they're going to be in trouble because I have to certify people. I will decertify people's attendance if they don't show up. Can we do an attendance sheet? Good? Yes, you'll do it. Please make sure to write your name clearly on the attendance sheet. I will warn everyone else who's not here that if they don't come, I will tell the registrar that they're not in the class. Okay. So let's look at the integral of f of t prime d prime. And let's take the Laplace transform that from 0 to t. Notice I put a t prime in here rather than t. Just somebody will finish the sentence. I put a t prime in here instead of t because you can't have the same variable in the limit as in the integral. Because once you integrate it, it's gone. Question?
Is this number 8?
Oh, I did.
And do these numbers correspond to the table below?
Oh, these numbers have nothing to do with the numbers in the table. These are just the order that I'm doing it.
No, that doesn't matter, but.
They're just trying to separate one problem from the next, that's all. It
Okay.
has nothing to do with the numbers in the table.
We did 7 already.
So this is the integral from 0 to infinity, e minus st. Notice this thing depends on t now, because once I integrate out t prime, I have a t here. So I have the integral from 0 to t, f of t prime dt prime. Now if I want to do this, the way I'm going to do is I want to switch the order of the integrals. And that's again, each integral is a limit, so I have to appeal to Fellini to be able to do that. I'm going to assume I can't do that. So let's just notice how to do that. So notice if this is t prime and this is t. So right now t prime is the inner integral and t is the outer integral. I'd like to switch it. Let's notice that here I'm integrating from 0 to t prime is going from 0 to t. And then t is going from 0 to infinity. So this is the region that I'm integrating over. So if I switch this, so if I want to make it the integral dt prime, the integral dt, f is a function of t prime, e minus st is a function of t, then notice if t is the inner integral, t is going from t prime to infinity, t is going from t prime to infinity, and t prime is going from 0 to infinity. I'm sorry, do I have that right? Yeah. T is going from t prime, no, it's going from, t is going from, let's get this right. T is going from 0 to t prime. Do I have that? That doesn't look right. Which is the inner integral? T is the inner integral. And let's just make sure I got this right. So here, t prime went from 0 to t, and t went from 0 to infinity. And now what I'm doing is I'm doing t is going, t is going, let's do it, t prime. Let's do this right. T prime is going from 0 to t. T prime, I'm doing it, I did it backwards. This is t prime. Okay, so t, we said t prime is going from 0 to t. T prime is going from 0 to t. That's correct. And t is going from 0 to infinity. Right. I had just gotten the t and the t prime backwards. Now let's, that's in the upper one. In the lower one, I have t. So t is going from t prime to infinity. And t prime is going from 0 to infinity. Finally. Okay, so let's do that. I have the integral from 0 to infinity, t prime, f t prime. And now I integrate this. I have e to the minus st over minus f over s, where I flip the limits. So I go from infinity to t prime. dt prime. I already have the prime there. Well, at infinity, this is 0. So this is, at t prime, this is just the integral from 0 to infinity, dt prime, 1 over s, times e to the minus st prime. Because at the upper limit, it's just dt prime, times f t prime. And notice that this is just f tilde of s. So this is just f tilde of s divided by s. So notice there's an almost a symmetry here. The Laplace transform of the integral disappeared, and I get a 1 over s. The Laplace transform of the derivative disappears, and I get multiplied by s. But I still have this minus f of 0, which I don't have here. So it's not an exact symmetry, but it's close. But you can see that when you start dividing by s, that came from integrals, and when you multiply by s, that came from derivatives. So you can already see that if I have a differential equation or an integral equation with derivatives and integrals, then Well, then that's going to be, if I have derivatives and integrals, all of a sudden when I transform, the derivatives and integrals are going to be gone, and I'm just going to have something algebraic in S. So that's a lot easier to deal with. So why don't we look at an example? And let's look at an example that we did previously by the old method, where we did a lot of algebra. So here's a CSTR with the first order reaction, product, constant density, so RA is minus KCA. And I've got to feed CA in. And of course here I have CA coming out. So we wrote our Governor equations as dCA dt is equal to CA in, that's coming in, minus CA over tau minus KCA. And we solve this as a first order linear differential equation beforehand. So if you remember, we wrote this as dCA dt plus CA times 1 over tau plus K. Where we noted that we could write this as 1 plus K tau over tau was equal to CA in over tau. And then we appealed to the equation I had up there for about 2 weeks, which is the solution to a linear first order differential equation. Well, let's do it a different way now. Let's Laplace transform. So if I take the Laplace transform of this, well, when I have a derivative, that turns into S CA tilde minus CA of 0. And what do I have here? I'm sorry, I should do one thing. Before I do this, before I do the Laplace transform, we subtracted, I want to do one more step before the Laplace transform. We subtract the steady state condition. So I have dCA t less than 0 dt, we said was 0, plus CA of t less than 0, 1 plus k tau over tau is equal to CA in for t less than 0 divided by tau. And when we subtract, we got dCA prime dt plus CA prime times 1 plus k tau over tau was equal to CA in prime over tau. And the only difference between this equation and this equation is my initial condition, CA prime of 0 is 0. That is, the initial condition is 0 because CA prime is the value at 0 minus the value at 0. So now let's do the Laplace transform. If I do the Laplace transform of the derivative, I get S times CA tilde, S times CA prime tilde, minus CA prime of 0. But we just said CA prime of 0 is 0. And then I have plus CA prime divided by t. Because remember, this thing we said is 1 over t. Is equal to CA in prime divided by tau. Tilde. So I have a Laplace transform every term. I have a Laplace transform this, and I got S times the derivative times the tilde minus the initial condition, which was 0. This was a constant, so when I Laplace transform CA prime, I just got CA prime tilde. And this was 1 over tau times the Laplace transform of CA in prime. So let's see what we get here. So notice that this thing, I can factor out CA prime tilde. And this is times S plus 1 over T. So I've got S plus 1 over T, which is S plus 1 over T. And what's S plus 1 over T? This is equal to CA prime tilde times 1 plus ST over T is equal to CA in prime tilde over tau. Well, let's solve for CA prime. CA prime tilde is equal to T over tau 1 over 1 plus ST times CA in prime. So I just did a little bit of algebra. Now let's figure out CA in prime was a given. So let's see what I know about CA in prime. We were given that CA in went from one value to another and T is equal to 0. So CA in prime, well that was CA in. So CA in prime is CA in of T greater than 0 minus CA in of T less than 0. So that's equal to so it's 0 for a while. For T less than 0, it's 0. And then it jumps to delta CA in. So this is just equal to delta CA in times theta T. Is that clear? I had a step function. Since I have a prime, it's 0 for T less than 0. And for T greater than 0, it's just delta CA in. So that's exactly my step function, my theta. And the Laplace, so therefore the Laplace transform CA in prime tilde. Well, this is just a number, delta CA in. And the Laplace transform of theta, where is it? The Laplace transform of theta is just 1 over S. So we're ready. Now we can go back to this equation. Now we see this is big T over little t. What's big T over little t? Big T is tau over 1 plus k tau divided by tau. So it's just 1 over 1 plus k tau. Times delta CA in times 1 over 1 plus S, 1 over S times 1 plus S tau, ST. So this was an algebraic equation, we solved it. And let's notice something. This thing, we said, is just CA, is just the steady state value of CA over CA, CA over CA, CA is less than 0. So this is the steady state value of CA of T over CA of T less than 0. Just the steady state value. And let's try to convert this. So if I have CA prime of T, what do we get there? I have a 1 over S times 1 plus ST. If I look at my table, which you don't have in front of you, but I'll photocopy for you next time, we can notice that line 5 of the table says, what does line 5 say? It says that if F tilde of S is equal to AS plus 1 over S times 1 plus ST. Then f of t is equal to 1 plus a minus t over big T times e to the minus t over big T. And where's the parentheses? Here. Yeah. So that's line 5 of the table. So let's notice that, well, let's write the constants. The constants come along for the ride. Delta CA in over 1 plus k tau. And 1 over s, this denominator here, is this when a is 0. So when a is 0, I just get 1 minus t over t e to the minus t over t, which is the same answer we got last time. Actually, I think I lost something. It's a minus tau, not a minus t. It's a minus t. So when a is 0, I have the t's cancel, and I'm just over the minus sign, and e to the minus t over big T. Are there any questions on that? Questions? I realize there's a fair amount of algebra, but most of the algebra shouldn't be too difficult. Questions? All right, now, if you remember last time, we not only did one CSDR, we did 2 CSDRs in series. So I have CA in, CA1, CA2. Now, we've already solved for CA1. That was the problem we did before. So let's notice if we want to do CA2, we have the exact same equation, but CA in is replaced by CA1. So let's notice I have dCA2 dt is plus CA2 times 1 plus k tau 2 over tau 2 is equal to CA1 prime divided by tau 2. It's the exact same thing as this, because it's a CSDR, but instead of CA in coming in, I've got CA1 coming in. So it's the exact same equation, but this is my equation. Is that clear? It's the exact same equation I had here, but I have this. And now, again, I have that CA1 prime is equal to 0. Because by definition, a prime at 0 is 0. So let's Laplace transform this. If I Laplace transform this, I get the exact same algebra as I had here. The only difference is instead of CA in prime, I have CA1 prime. So by the same algebra, I have CA2 prime tilde is equal to T2 over tau is just 1 over 1 plus k tau 2 times, and then I have a 1 plus ST2. So I'm just copying from here. It's the exact same algebra, but now I have, instead of CA in prime tilde, I have CA1 prime tilde. But up to here, it's exactly the same algebra. No need to do it again. But now, instead of CA1 prime tilde being just a Heaviside function, I take it from here. I know what CA1 prime tilde is. CA1 prime tilde is just this. So this is equal to 1 over 1 plus k tau 2. 1 plus s t2. And now I have a CA1 prime tilde. Let's copy it from here. It's 1 over 1 plus k tau 1 times delta CA in divided by s 1 plus st1. Are you following me how I did that? I did it, it's exactly the same algebra, but instead of a CA1 prime tilde, CA in prime tilde, I have a CA1 prime tilde, CA1 prime tilde. And CA1 prime tilde I just copy from here, or from here. So I've got the 1, the s times 1 plus st1, the delta CA in, and the 1 over 1 plus k tau 1. So all this all the circled stuff came from CA1 prime tilde. And the other stuff was just copied from here. 1 plus k tau 2 and 1 plus st2. So now I've got a bunch of constants. These are constants, this is a constant. But now the denominator, I have a s, 1 plus s tau 2, 1 plus st1. So there are two cases. One case is where the volumes of the reactors are the same. So case A, if V1 equals V2, then tau 1 equals tau 2, and T1 equals T2. They're all the same. And then this denominator, the important part, the denominator, is 1 over s, 1 plus st squared. And let's see what happens there. If I do that, I have to look at my table, and wouldn't you know it, line 8 of the table. Line 8 of the table. I need more space. So can you take a picture of that board, and I'll erase it. So line 8 of the table says, let's copy line 8. That says f tilde of s is as plus 1 divided by s 1 plus st squared. That corresponds to f of t is equal to 1 plus a minus t over t squared times t minus 1 e to the minus t over t. So let's look at what we get here. So this tells me that CA2 prime is equal to. Okay, I've got 1 over 1 plus k tau squared, because this is case A, where t tau 1 and tau 2 are the same, times delta CA in times, I think that's all the constants I have, right? Yeah. And now I just plug this in. Notice I don't, A is equal to 0, because I just have a 1 over that. So when A is 0, I have a 1 minus, okay, when A is 0, I've got minus t over t squared is 1 over t squared. Why do I have a minus 1 there? That's not minus 1. It shouldn't be there. No, it is there. Okay. All right, so let's see what we get. So I've got, so I've got a t 0, and here I have a minus t over t minus 1 e to the minus t over t. sure I have the parentheses in the right place. Yes. Okay, so, yeah. So there I have CA2 prime. And notice that I can rewrite this as delta CA over 1 plus k tau squared. And here I have a 1, and then I have a plus e to the minus t. I guess I could just leave it the way it is. So, and I have the minus sign in the right place. This is line 8. No, there's a plus here, not a minus. Right. So then I have, I guess I can just leave it, but here I have a 1 minus e to the minus t over t plus t over t e to the minus t over t. Now, again, I think I have this sign wrong. There was a minus sign here. So let's go through this again. A is 0, so here I have a minus 1 over t times t, and a minus 1 there. And then I have this. That's starting to look better. Or I could just factor out the minus sign here, and then these are plus. And that looks correct. So let's look at delta CA in over 1 plus k tau squared times 1 plus 1 minus 1 plus t over tau. Actually, this is fine. I just leave it the way it is. Okay, so let's notice what happened here. Notice that I have the exponential decay, but I also, because I have a resonant condition, I have t times an exponential, which is what I got last time. Let's look at case B, where V1 is different from V2. When V1 is different from V2, I have 1 over S times 1 plus ST1 times 1 plus ST2. So if I look at my table, I look at line 10. Line 10 in the table, again says, when f of t, f tilde of s, is equal to as plus 1, divided by s, 1 plus st1, 1 plus st2, that corresponds to f of t of 1 plus t1 minus a over t2 minus t1, e to the minus t over t1 minus t2 minus a over t2 minus t1, e to the minus t over t2. So there I've just copied what's in the table, and now let's write that one. So here we have, in case B, I have CA2 prime of t is equal to, well, I've got a delta CA in over 1 plus k tau 1, 1 plus k tau 2. That's what I had over there. Those are the constants. And now, from this denominator, a is 0. So what I get here is I get 1. When a is 0, well, I just drop a. So I have t1 over t2 minus t1. And actually, let's just factor out the 1 over t2 minus t1. So I've got t1 e to the minus t over t1. And here I have minus t2 e to the minus t over t2. And there I have the solution, both for case 1 and case 2. And I want you to notice how much less writing that was, how much easier that was than the way we did it previously. We had lots more writing. And you can check that this is exactly equivalent to what we got last time. Are there any questions on that? Questions? Any questions? Okay, let's do a couple more properties back to properties of the Laplace transform. I don't know, I think we were up to number 8, if I'm not mistaken. 7, yeah. So number 8, if I have a time lag. So, and that happens a lot in control. You press a button, and it takes time for the effect to happen. So I want the Laplace transform of f of t minus some value alpha, where alpha is the time lag. So let's see what that is. That's equal to the integral from 0 to infinity, f of t minus alpha, e to the minus st dt. Well, f is a function of t minus alpha. So I'm going to change variables. I'm going to let t prime be equal to t minus alpha. And dt prime is dt. And then I get this thing is equal to the integral f of t prime, e to the minus s, well, t is equal to t prime plus alpha, dt prime. And let's notice that when t is 0, t prime is minus alpha. And when t is infinity, t prime is infinity. But what I had written here on the previous board was one assumption of Laplace transforms is that f of t is 0 for t less than 0. I'm always assuming f of t is 0 for t less than 0, in which case the lower limit I can set to 0. Because f is, for negative arguments, just equal to 0. So this thing is equal to, it's equal to the integral from 0 to infinity, f of t prime. And now I have e to the minus st prime, dt prime, times e to the minus s alpha. Because an alpha is a constant, so I can pull it out. So this is just equal to, and this is just f tilde. So it's e to the minus s alpha times f tilde of s. Any questions on that? I guess we're going to do one more property today. And this is called the final value theorem. And this says, suppose f tilde of s is continuous for s greater than 0. Yep. I'm sorry, which one? Time lag. So here I'm looking at the Laplace transform of a function of t minus alpha. So think of the following. You flip a switch, and instead of things changing immediately, it takes alpha seconds for things to switch. So f of t minus alpha is what happens after time alpha. It doesn't happen from 0, it happens from alpha.
Right, so we said the Laplace transform had f of t minus alpha e to the minus st.
Yes.
But then we saw that if we had e to the minus st prime.
Yes. So e to the minus, but t is equal to t prime. T is equal to t prime plus alpha from here. So I plugged in t here. dt prime is dt. And f now, t minus alpha is t prime. So is this step clear?
Yeah.
And now I factor out the e to the minus s alpha. I can do that. This is just a constant. And I noted that f is 0 for negative values of the argument. So I can just turn this into a 0. And that's how I got this. And so this became a 0 to infinity. F of t prime, e to the minus s t prime, e to the minus s alpha dt prime. This thing is just f tilde of s.
So we have t prime in the exponent of the e, and we have
Right, and I have a t prime here and a dt prime. T prime is a dummy variable, so when I integrate it, I can call it anything I like. I can call it Harry, d Harry.
But we said it's going to be t minus alpha, right?
Yeah, the alpha is out here.
So you would have to include that in the f tilde s. If you're saying f tilde s is equal to that integral,
Well,
then
remember, this thing here is f tilde of s because there's no alpha here. The alpha is sitting outside. So this came along for the ride, and this box gave me an f tilde of s.
I guess I'm confused because the original f tilde of s that we defined had a t, not a t prime, in the numerator of the e.
Uh-huh.
So I see
You're talking about this definition.
Yeah.
Yes, but I can always, remember, the answer is a function of s. It's not the answer is a function of s. The answer is no longer a function of t, it's only a function of s, because I've integrated t out, because t is the dummy variable. So instead of calling it t, I could call it Harry, or anything I like. So I have e to the minus s Harry d Harry. Here I called it t prime. It doesn't matter if I call it t prime, t, Harry, it doesn't matter, because it's integrated out, it's out of the problem. So the answer only depends on s. It has no t's and has no t primes.
Okay.
Is that clear?
Yeah, that makes sense.
Make sure to ask those questions, because I want you to understand this. Do you have a question? Okay. Okay, so let's assume f is continuous for s greater than 0. Then, the limit as t goes to infinity of f of t is equal to the limit as s goes to 0 of f tilde of s, which is kind of cool. It says that if I want to know the steady state value, what does that say? If I'm going to go to steady state, before we prove this, if I'm going to go to steady state, it's going to take, at worst, infinite time. I might go to steady state earlier, but certainly by infinity I should get there. This tells me I don't even have to invert the equation. I went through the trouble of doing these inversions to get the time dependence. If all I'm interested in is the steady state result, I don't have to invert. I just take f tilde and set s equal to 0. Isn't that cool? I don't even have to do the inversion. So, but the hour is over, so I can't prove it. I'm going to have to prove it next time. But what I can do is just look at the solution here and apply this. So let's note that CA1 prime tilde as t goes to infinity, steady state. I just set s equal to 0 here. Just set s equal, I'm sorry, it's not f of s, it's s f of s. So I multiply by s, the s's cancel. I set s equal to 0, I just get delta C again over 1 plus kt. How about CA2 prime tilde? Actually, CA1 prime steady state. I've got case A and case B. In case A, here was case A. Where's case A in? Case A, yeah. I multiply, so I have to use the Laplace transform, right? CA2 prime tilde. I multiply by s, actually this is for all of them. I multiply by s, the s cancels, and I set s equal to 0. So this just becomes 1. So I delta C in over 1 plus k tau squared, and for case B, it's delta C in over 1 plus k tau 1, 1 plus k tau 2. So the steady state, I don't even have to invert. I multiply by s, and I say s equals 0. The s is canceled, and these just become 1, and that's all I get. So it tells me that this coefficient here is the steady state value. This is the steady state value, and notice the last thing before we finish, CA2 prime steady state divided by delta CA in, which in this case is 1 over 1 plus k tau 1, 1 plus k tau 2, is what we call Kp, the steady state gain. It's the change in the output over the change in the input. It's a steady state gain. And I get it directly from the Laplace transform without having to invert. I'm trying to get you to like Laplace transforms. Laplace transforms are your friend. Are there any questions? We'll prove this next time. It's a one-line proof, but I think we did enough for one day. Questions? Make sure you sign the attendance sheet. Let's see how many people are here today. 3, 6, 9, 12, 15, 18, 21, 24. So it's 42 students in the class and 24 are here. So we just changed the digits around. Are there any questions? Again, for those who came in late, the exam is a week from Wednesday. I have office hours today, which is Monday, from 5 to 6. No one has come to office hours since the first week. I don't bite. Now, next Monday is Columbus Day, so I don't know if there'll be office hours on Columbus Day. We can set up a recitation sometime in between if there's demand. You have to tell me there's demand. I don't want to set it up and then no one shows up. Any questions?